So the geothermal energy basically may mean that you have hot ground very close to, we always have hot ground everywhere in the world. We are sitting on molten lava. But the crust of the earth sometimes is thin enough that that heat becomes so accessible to us. Okay? So before you start being envious of the people that have sauna on their background, you need to know that those people that have sauna on their background are also the people who have volcanoes and earthquake. So that's not a good place to live in. And you can see how there is like, so I'm originally from Egypt, and so we had this over here, and when I was like in college undergrad, we had this major earthquake, 5 point something, and man, that was the most scariest moment of my life. We live in a high rising, not really that high rising, it's like 5th floor, okay, and it's a concrete building. And I was sleeping, my sister was sleeping, my mom and dad were at work till they come late, and I woke up to the building shaking. And I'm so proud of myself. I ran to my sisters rather than running away from them. I ran to the room, and they were like in their bed, scared, and the building was really shaking. And I just rushed to the balcony, and I don't know what did I see, but I came back, told them, don't worry, it's an earthquake, as if that's okay, like it's not like a bomb or something. Don't worry, it's an earthquake. But then the building started to shake really, really loud. It was like almost a minute of torture. And so I told them, let's run downstairs. And so we went onto the stairs, and just when I went out to the house, I remember I don't have my key. And I went back to my room to get my key so I can lock the door. And so by the time I came down, while I was going down the stair, the building was reshaking, and the noise of the concrete with the steel bars when they shake, man, so loud. And the frequency also is like tack, 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 tack. And so when I went, actually I was the last one to leave because I went for my key. And everyone was already sitting, all the women and the girls and the boys were like, the grown-up were like at work, but the children were down. And bunch of people, all the houses died. So what I'm trying to say is that it's a double blessing to sit near those ridges, yes, you get hot water. And actually, so over there is a place where hot water come, and people go for it for medication stuff, just like over here in Arkansas also, I don't know why it's not soon over here, but in Arkansas there is like where President Clinton was born. What is the called of the city? Hot Springs? I think he was born in Hot Springs. I mean, we visited there, and they have a lot of places that it used to have a lot of hot water coming from the ground, or at least like mineral water coming from the ground, and people use it for medication and stuff. Anyway, so when you are in a place like this, for example, Iceland, you got yourself a really nice hot tub in your river, right? And on the back over here, those are actually steam power plant that rather than burning natural gas to generate electricity, they are just using the hot water to generate electricity. So the fuel is coming for free. Hot water, and we will see how you can make steam out of it and run a turbine. And you are done. Actually, New Zealand is 100%, almost 100%, running on natural resources. 73 hydro, because they have a lot of waterfalls, and the rest is 26% is coming from this. Okay, maybe 0.1% fossil. So they are living for free, basically, and still they bankrupt their country a few years ago. So that is amazing. If you're living for free, why would you bankrupt the government? Anyway, so when you have all those hot water in, sometimes you don't even have to dig for it. Sometimes it come out like geysers, right? The hot water will come for you. And even better, if it come as a steam rather than water, then your job is done. You just connect, hook it up to a turbine, right? So the places in the US that are really lucky like this, you can see the color, and in Oklahoma you can see we are, we are not dark orange, but dark red, but we are still decent. Okay, I mean we are better than Michigan, or better than those people because they have mountain, right? I mean a little bit hilly maybe, but you can see how the Earth become really very hot, very close over here. Okay, and what is the red dots? Those are places where it's hydrothermal site. What's hydrothermal? Not only the ground is hot so close, but also there is water on top of that hot ground. So those are the places where you just open, you tap, and steam come out. Okay, so I mean in Oklahoma, we don't, I guess, since hot springs will be here. So you are not gonna tap and get hot water, but the ground is warm. Right? So here is what you do with, why do we have hydrothermal? So the reason why we have hydrothermal is this: you got this hot lava over here, so close to the place where the water is. Why the water is sitting over here? Rain, over the years accumulate and fill that reservoir. So now if that reservoir have a chance to go outside, or if you're gonna dig for it yourself, drill for it, or maybe he will come itself, you got yourself steam coming out. So hydrothermal means water on top of a hot location. Okay, and so when this is the case, whether you're gonna get steam directly or you're just gonna get hot water, either way, we will see how we can break that hot water into liquid and steam. So we had steam, we are lucky, we are done. We had hot water, still good enough. We will break it into vapor and liquid, and the vapor into a, what do you call this cycle? Steam turbine, condenser, Rankine cycle. This is just like a Rankine cycle. So a Rankine cycle sit there, and you get your electricity out of it. Okay? We will see that here's the diagram, and we'll probably have a homework on this too. Okay? So now, so hydrothermal, water and hot rocks. Geopressurized, that's when there is water, but the water is like really either not really hot enough to make steam, or it's just so salty that you are not gonna really try to get steam out of it. So either way, it's hot resources, but it's not really gonna give you steam to your turbine. Okay, either because too salty, or it's not hot enough. So what we do with it? We will still use it. There's something called binary cycle that we will still manage to use it. Okay. So this slide is about the fact that geothermal energy is renewable energy or not. So renewable energy is like sun and wind. It's always there. You put the turbine and it will run for, the next 100 years. As long as this wind turbine runs, this thing will run. So is geothermal energy renewable or not? Yes, it lasts only for so long because, one, you could run out of water, right? I mean, if this water you are using it and dumping outside, you run out of water. And over here he's saying, well, in order to address this depletion problem, maybe you need to inject the water back in, or you can even inject wastewater from other places. And so he's talking about project that we will basically take the water from lakes and stuff and they dump them in, so that the site where the steam is coming don't ever run out of water. But even if you take care of that water problem, there's another problem, which is those rocks that made that water that hot, to the fact that to the extent that it made steam, are actually gonna run out of fuel. They get cooled down because of all that cold water you're sending back in. So I know that you would think, how is that possible? The Earth is still really hot under. Yes, but the conduction, that energy transfer that made that place that hot took time. Okay, and they tell you like in 50 years, maybe the site will be depleted from the energy in it. So this is not really a big deal because there is no power plant that will survive 50 years anyway. So it's just that, you know, by the time the turbine has to be decommissioned and the boiler has to be decommissioned and everything is like, you know, like right now, Jinx, for example, power plant, you know, it's like the utilities was built in the 70s, and it's very hard to find parts. If anything break in the turbine or the boiler or something, it's very hard to find parts because, say, Westinghouse and GE stopped making those parts. So they have their own machine shop to make parts on the spot for anything that break. And you can do this you can push the life of a plant for a certain number of years, but then after a while, no, you really have to decommission the site. It's not going to work anymore. And so by the time you decommission the site, because of the plant and the equipment, the ground also will be almost done. So they tell you, great, don't just put another plant in the same spot. Just move and put it in nearby place. And so that's how it works. Okay, so, but the water, that is a serious problem. Okay, and so you always need to make sure that water go back into the site so that you don't run out of water. So there are two ways to extract energy from those hydrothermal sites, okay? Or geothermal in general, whether it's hydrothermal or geopressurized. So 1 year, I just asked them to plot the cycle on the TS diagram. So you need to be very comfortable with why things the way they are, okay? So what is going on over here? He's saying that he's getting actually steam. So this is actually steam. So the steam maybe have just like some particles hanging on it and you don't want to send it to a turbine. So they have like centrifuge, centrifugal separator that clean the steam, but then it's ready for the turbine. And once it goes in the turbine, so you are getting the stuff over here, saturated steam. If it's liquid, it would be here, right? This is the TS diagram. So liquid will come over here, vapor will come over here, right? So if you are lucky and you are getting it over here, you already have steam, you just clean it. And so what is that line? What do you think this line is going from 1 to 2 to 3? Is going 1 to 2 to 3. What do you think happened as we are going through this? Heated up a little bit? No. Why would you get heated up a little bit? That should be the opposite. It should get cooled a little bit. It's leaving the hot place. Right? It's like you're taking your pizza out of the oven. By the time it go to the table, I mean, it cool a little bit. But it's not the cooling. Let's assume the pipes are insulated because they should. I mean, that's their money. If you, it's like if you have hot water coming, you need to wrap the, and they do, they wrap the turbine and they wrap the pipe. So the steam going from the boiler to the turbine in any power plant, the pipes are all insulated. Otherwise, everyone will be fried in the control room because that steam in a big power plant come at 1,000 degrees Fahrenheit. Okay, so you don't want to sit next to a 1,000 degree Fahrenheit pipe. You don't want it in your building. So they wrap it with insulation. So what happened then if it's not heat transfer? What happened in a centrifuge, in a centrifugal separator? What happened in pipes? What do you think this line is? Constant, huh? Yes, throttling, constant insult. So you are choking the flow, kind of like there's pressure drop from 3 30 bar, to say 2 bar, 2.5 bar, sorry, 5 bar, because 1 megapascal is 10 bar. So you are dropping the pressure, tuck, 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 but at constant H. Why constant H? What's my proof? It's constant H. What is my proof? My proof is that, so here is the cycle, this is the TS diagram, right? And so he's coming at P1, B2, P3. So during this journey, and that's indeed just nothing but, a chamber where things just like spin like this, and so the big stuff fall, right? Actually, maybe I need to make a better drawing. So it would be something like this, and you go with tangentially like this, and so they do that, and then say you pull this out over here, and all the bad particles, they just move by the centrifugal force to the sides, and then maybe you can collect them from the bottom after a while. But if this is my control volume from the time he come to the time he leave, the first law would say Q dot minus W dot equal to M dot delta H. Work is 0, Q is 0 if you did a good job. Delta H is 0, which means H1 equal H2 equal H3. Make sense? No work, no heat transfer, enthalpy remain the same. Okay, so we come over here at, say, a pressure of 0.5 megapascal or something. Then what? We send it to a turbine, right? And the turbine expand like this. So from 3, let's call this 4S, but the real 4 would end up being like maybe something like this. So there is the isentropic expansion, and there is the real expansion, right? And of course, S3 is the same as S4, right? That's what we mean. Ouch. What happened? Give me my thingy. So we were saying that S3 equal S4S, right? That's isentropic expansion. So the whole idea behind those problems is once you plot the cycle on the TS diagram, you should be able to get the H of each one of them. So the first step after writing what's given and what's required, the solution is to get the H of every one of those guys. Once you have all the H's, you'll be able to get the work, you'll be able to get the efficiency, you'll be able to get everything he asks you for. So a point like this, how can I get H1? What do I need to get H1? Yes, I need two property, right? So if I know B1, and I do know B1, and I know that it is he will tell me it's saturated vapor. So that basically means that it's sitting on the line, huh? So P1 and it's saturated. So I will immediately get H1 equal to H1G. Remember, things on this side is called G, things on this side is called F, right? So we got ourselves H1G, and then we would say, well, H2 equal H3 equal H1. Okay, and we got ourselves H3. That's really important for the turbine. Now, to go from 3 to 4, first we go to 4S. And saying that S3 equal S4S, and knowing before, he will tell you what pressure is the condenser is sitting on. He'll tell you the condenser is sitting at, 0.07 bar or something. So you know B4 and you know S4S. And this will allow you to get H4S, right? This point, the point directly under 3. That's nice, but we need 4, not 4S. What actually happened is 4. So how can I get 4 once I know 4S? Help? How can I get H4 once I know 4S?
Don't we need quality?
The dome quality, no, you don't. So if you are saying, do I know X4S? Yes, X4S is actually, that's how I'm from S4X, you will be able to get S4S. Okay, and that quality at 4S is how you can get H4S, because that H4S is actually H4F plus X4S multiplied by H4, ouch, multiply by, my hand, go in the room, please. Multiply by H4FG. Okay, so what is that? That HG minus HF at 4. Okay, so this is a formula. This formula is how you can get the enthalpy for anything sitting in the dome. Yes, so I mean, if 4S is over here and you're saying, what is the H? You got yourself HG and HF, right? And the difference between them is HFG, and that's how you calculate the X4S, sorry, H4S. But the question is, what if 4 is actually over here? Huh? How can I calculate H4? Yes, yes. So see that the fact that this guy go this way and this guy go that way, that is related to the isentropic efficiency of the turbine. So he will tell you in the problem, or you will assume what's the isentropic efficiency of the turbine, and that eta turbine isentropic is small work over big work. That's what efficiency are. Small number over bigger number. So that we say it's 80%, 90%. What is a small number? Actual or ideal work? Actual is going to be smaller. So that eta, whether it's 85, 95, is H3 minus H4 over the big one, which is H3 minus H4S. So this is given, this is, you just calculated it. So the only thing that you don't know in this equation is H4, and you will be able to get H4. Okay? So back again over here in the cycle, we got ourselves, how much did we get the steam at? which is the same as H over here. Isentropic expansion, we get 4S, then we get 4 based on the efficiency. Now, what is over here? The book doesn't even care. Sometimes, what will happen over here? Let's go to the cycle to see. What do you think will happen after we condense? We have to bump it back, right? We have to bump it back to the ground. We have to bump it back to the ground. So here is 1, 2, 3 expanding to 4S, and this is 4. And then we condense to 5. And so after we condense to 5, he does not show. So this is a weird condenser, which I'm gonna explain it to you in detail. But the point is, after we condense, we pump and we send it back to the ground. Okay. So why do we have to pay energy on this pump? Why can't, I mean, we're gonna send it in the ground. Why can't we just send it in the ground without the pump? Yeah, because that came at 3 megapascal. So in order to bring it back, and where are you right now? You are in vacuum. How come? It's vacuum, right? Because 15 kilopascal, all condensers are sitting in vacuum. Why? Why we take the condenser all the way down to 15 kilopascal? So 1 atmosphere is how much kilopascal? 101 kilopascal. This is 15 kilopascal. We are 75 kilopascal down than 1 atmosphere. So, I mean, even if you want to throw this in the river, I'm not going to do it to 3 megapascal downstairs. I just want to throw it in the river or the lake and let the people swim in it. I can't because it's at vacuum. So why did I go to vacuum? Why I cannot just let it go to 1 pascal? Sorry, one bar. Why did we have to expand all the way down to this low pressure? Yeah, so that the turbine have room. As a matter of fact, you want the turbine to have the maximum pressure difference across it as possible, right? So for the Rankine cycle to really give you their best, this is important to remember. For the any Rankine cycle, which they all look some version of this, right? You get the steam somewhere. This is the TS diagram. You get the steam here from somewhere, boiler, steam from the ground, nuclear reactor, I don't care. Something will give you steam. Of course, if it's geothermal, don't expect superheat. You're lucky if you get saturated steam, right? I mean, this only in like when you are burning natural gas. Even nuclear reactor, you will get here. You're not gonna get superheat. So you expand, whether from this point or this point, right? And then you condense, okay? And once you are saturated liquid, you bump back again to the pump. You bump back again to what? To the boiler pressure. Whether the boiler is your reactor or your gas-fired furnace or the ground, you need to bump back again to the boiler. So you return it to the boiler so that the boiler does not run out of water, right? So we have to go again to the, but my point is then for the turbine to get you all that work, you need this huge pressure difference, right? And so on the top, people actually try to go even above this. What is that point? The top point on the dome is called what? The critical point, right? So people even try to go above it. And that's like the Jinx power plant that we have across the river from my house. So they call this super critical. And they don't want to call it boiler anymore. At this point, they get offended if you call it boiler. They call it supercritical. Supercritical what? Steam generator. They tell you it's not a boiler, it's a steam generator. Why? Because to boil, you need to go from liquid to gas. Well, aren't you going from liquid to gas? Yeah, but you don't happen by bubbles, because above the dome, the liquid and the bubbles, the liquid and the gas or the vapor, liquid and vapor don't have boundary between them. So this is the same thing for liquid rocket engine. So I visited Edward Air Force Base a few years ago, and my research is a lot about taking images of atomization and sprays. They do 3D imaging. And so they were like complaining how it's super hard to take pictures because there is no liquid and vapor. There is just like this thing that is liquid and vapor. There is no wall between them. There's no surface tension that basically tell you this side you are liquid, this side you are vapor. You when you take a picture, you become black. It's like things that are diffusing in each other. So there is no wall basically between them. Anyway, so what I'm trying to say over here is you want to go as high as possible. And when they do that, that is like the Cadillac of the steam generator. They wouldn't call it supercritical. They would call it, if you go really that high, it's not supercritical steam generator anymore. It is ultra critical, right? That is the Cadillac of the steam generators. Of course, that means very expensive pipes to take that pressure with that temperature, right? Very steam, like it's really expensive. But why they are doing this, efficiency really increase. Now it's not just the work is increasing, but it is also the efficiency. Amazingly, the efficiency also increase. Okay, it's not just the kilojoule per kilogram because look at my turbine running all this big range. It's also the efficiency. Okay, so now from the top, we will take it as high as our material allowed. So all the professors and scientists working on material science, they want to take us higher and higher by making more and more material that can go up. And at the bottom, I want to take this as low as possible. How low can I get? I mean, why 15 kilopascal? Why not 7 kilopascal? What's my problem? Why I cannot go any lower? Can I go here? What do you think the problem downstairs? We also want to send it as low as we can. What is limiting us? I can't hear. So that is a question. What is the effort to take it down? What does it take to take it down? More work on the pump? You think? Yes, it is more work to pump from here than here. But guess what? The pump work is very little to the extent that in this chapter, in that book, he thinks the pump work is zero. And like, what do you mean zero? You are still need to pump, but like tell you it's nothing compared to the turbine. So whenever we are doing any calculation for research, and someone asks me about the pump, I tell them, just don't worry about it now. I mean, for order of magnitude, it's nothing. But of course, it is a pump, and it takes electricity and everything. But no, the pump is not the limiting case. Yes, it takes more work to pump from 0.07 bar rather than 0.15 bar, but that's not the deal. What is preventing us? It is worth it. It's worth every single. It's like every single minute you spend studying for this course will help you in your career. It's worth it. If you know the answer, you send it to an email to me and you get one free homework problem. Okay? What is limiting us from going down? Okay? So I think it's 8:49. So why don't we take 15 minutes break and we'll come back at 9:05. So restroom break, guys.
Most part, it's pretty fun. I feel like we're stuck. It's, we just keep going back to how we're going to do the full heat cut and then still water here. And we just, we're repeating going back and forth on that. Elevators. Oh, not, I don't know. Sorry, we got our feedback dumped out a few times, like we had this idea, dumped up around it, right? And, our little project champions have been all for it, but then all of a sudden he's just like, I don't know if he's just schizophrenic or just bipolar or what, but he just, all of a sudden he wants to go a different direction, and it's just, at this point, it's block, stop the block. At this point, kind of, we're getting kind of close to the point where we can't really just keep doing that. We have the same, we had our FDR, and we were with the designer pretty happy with it. It's like, okay, cool, it's functional, but it's ugly. I want you to like redesign this great. It's like, well, we've been going in this direction since our CDR. If that was a concern you had, that was the time to bring it up. Like, it's kind of lame game to almost start over design wise, but like, yeah, we dealt with a bit of that, and I'm just like, I almost feel like they're doing it on purpose. Like they're just trying to introduce you to the fact that you just have to keep iterating through these different designs until somebody's happy. I don't know. Just I just feel like they're doing it on purpose at a certain point, you know? It's like, I don't know. So we pretty much hit budget, and we need more money if it's low. Well, also looks like suddenly I said this, okay, we're talking about the issues of well, aren't you guys budgeted? I'm practicing that, but you get something that will every day. Oh, I can see that. say, I think all the comments, just allegations and stuff is up there. I think we'll bring in a extension cord here next time, if it's long. We don't gotta, let's say, run out of battery.
Remember last time?
Yeah.
It was America. I think it's a message. You would think, when you have a presentation, they give you some power outlet near you
Yeah.
to have a desktop, or something. But they have every single output taken. By what? I don't know. Either just like a screen, a computer, and the monitor. That should be 3. Why they are using like 7 or 8? Or what?
All right, I think we had enough for a break. Can you guys hear me online?
Yes, sir.
Thank you. All right, so we said that it's those hydrothermal sites will produce steam, will be over here saturated steam. You go through constant enthalpy line until you get to the right pressure, the pressure of the turbine. He will tell you the turbine is running from 0.5 megapascal and the condenser is running at 15 kilopascal. So you have this point, you go down here, you get the entropy. You tell yourself, I know the entropy, therefore I know the quality. And if I know the quality, then I calculate the enthalpy. You know the enthalpy over here, using the efficiency, we'll be able to get this H. And of course, the condenser will take the water, the wet water, all the way to saturated liquid. And that will give you 5. So H5 is simply HF at 15 kilopascal. Okay? And that's all the H's in the cycle. Yes, there are 6 over here, whereas like the pump will take you up to a certain pressure, and then you go to a cooling tower that will cool you down to 7, and then 7 is add over here. But this calculation doesn't do anything to do with the cycle efficiency. It's later we will use this, or we will do this in detail to figure out how much cooling water do we need, for example, or how large is the cooling tower. But as far as the cycle efficiency, what is the cycle efficiency? By definition, efficiency is work net over Q added. Yeah, work net over Q added, energy in. Work net is supposed to be this minus the bump, but you will see how you neglect the bump. Are we okay to neglect the pump? Yeah, I guess if the homework example or the book is neglecting it, so in the exam you can neglect unless we specifically ask for stuff over here. Okay, so work net then become work turbine, and it wouldn't really hurt you in the solution to say neglecting work pump because it's small. Okay, what is Q added? I get the H from them here, or this H, basically it's the same H. And I return back the stuff to them at, most of the time, we will return it at here rather than cooling it and then returning. Why would you cool it and return it? Doesn't make sense. So once you inject, you should send it over here. And in other books, you will see that you will inject directly here. There's no point, like if I'm sending my water back to the boiler, my boiler, why would I cool it? So you should send it directly from here. But anyway, so when it comes to Q added, it's this delta H. H3 minus H5. Okay, so what kind of question he could ask? He could say the efficiency, calculate the efficiency. He could also say what flow rate of steam is required, how much m dot is needed here to generate 10 megawatt. How much steam do I need to pull from that site to make this turbine run at 10 megawatt? The 10 megawatt that's coming out from here is m dot time, well, the 10 megawatt coming from the turbine. H3 minus H4S. If you say the 10 megawatt is m dot time efficiency, which is 82% of the turbine, 90% of the generator, then you multiply time the delta H ideal. But if you say it's m dot time H3 minus H4, that is H actual. So then you don't multiply by this H anymore. You just by this efficiency anymore. You just multiply by this. Okay, make sense? So here's the solution. So I'm saying how the efficiency of the turbine, how is it defined, right? And let's go through the solution, and then we'll come back to exactly what happened over here in detail. Okay, so here's the H. Again, the whole problem is getting H's, getting H1 that we said, setting H1 equal H2, H3, right? And going down to the isotropic 4S equals 3, and saying the pressure, then you will be able to calculate the quality from SF and SFG and S for S. You know that equation, right? What is going on here? Let me explain. So over here, he's saying, if someone wants to calculate this point, let's call this 4S. What is the quality of 4S? How can I calculate that? How do I get it? The only thing that I know is S4S equal to S3. So coming from point 3, going down for S, I got same entry. How do I get X4S? Help? Yeah. So I get what? What do you want me to get at the saturated points? I get what here and what there. What do you want me to read? S, right? SF and SG. And then tell myself that S4S is SF plus X4S time SFG, which is SG minus SF. This equation is how you can calculate X4S. And similar to it is the one that we wrote for the enthalpy, right? Once you know the X4S, then you could say H4S is HF plus X4S multiplied by HG minus HF. Make sense? So same equation that basically say anything in the dome, you want to get it, you will get it from adding SF to a portion of this, G minus F. How much? Depending on the quality. So of course, you guys remember that on a TS diagram, if you are here, what's your quality? 0. And over here, X equal 1. And of course, in between, you know, depending on how far you are, you go from 0.25 to 5 to 0.75 along the line. That is the quality, okay? And that's why those formulas. So the first one, we use it to calculate X4S. And the second one, we use X4S in order to calculate H4S. So we come here knowing S4S, and we come here knowing X4S. Right? So that's what he will do over here. See? This is for S, and he just calculate the X, and then he's using the X to calculate the H for S. Those are the two equations that we said. Okay, work ideal, work actual, which is work ideal time efficiency. Okay. And now to calculate the thermal efficiency. Calculate the thermal efficiency. What did we say the thermal efficiency is? Work net, which is this minus 0 over here, or whatever number is here, divided by Q added. So what is Q added? H1 minus the H that he's returning back to the ground. So here he's returning it at 7, which he would say 7 equal to 6 equal to 5, kind of. Everything is here. Okay. So I am fixing the book. The book is saying eta thermal is eta electric time work net. Well, that's not eta thermal. That's the plant. There's thermal efficiency of electrical production. That is weird. It's not called like this. It's either the plant efficiency or the thermal efficiency of the cycle. So when it's the cycle, we don't care about eta electric. When it's the plant, we put eta electric in it. So what I'm saying is that I don't agree that you should multiply by 0.9. If you want to put the electric efficiency in, then it's not eta thermal, it's the plant efficiency, the whole plant. But we agree on what? It's work net over Q added. And we also, I told you how his work net was just the turbine, no mentioning of any pump work. So he's like, forget about the pump. That's why. Okay, so don't be worried that he didn't use the pump. Okay, two things. There is something called the heat rate. I hope you remember it from thermal fluid. What's the heat rate? It's 1 over eta thermal. Okay, so if eta thermal is work net over Q added. So 1 over eta thermal, that's what would be 1 over efficiency become Q added over work net, right? If I say 1 over efficiency, it will be Q over work. And while the efficiency, which is work over Q, is less than 1, if I do 1 over efficiency, that has to be more than 1, okay? It's Q over work. So if the efficiency is 0.4, 1 over the efficiency will be 1 over 0.4, right? That's 2.5. What is that number then? Q over work. That is how much heat the boiler is using divided by how much work the turbine is making, electricity the turbine is making. So when they do it like this, and especially if you actually do it with eta electric too, then you get, and also especially if you multiply this 1 over eta times 3,412. What is that magic number? That's how many BTU per kilowatt hour, basically. It's like 3,412 BTU. So what happened is basically when you do this, you turn the work to kilowatt hour, and you turn the Q added to BTU. So both of them actually was supposed to be joule per kilogram and joule per kilogram. But that number, right? Because efficiency is dimensionless. When we say the efficiency is work kilojoule per kilogram divided by Q added kilojoule per kilogram, I get 0.15 period. There's no units next to it, right? The efficiency is 15%. We are done. No units. But when you say 1 over 0.15 and you multiply by 3,412, then it becomes BTU per kilowatt hour. That number is super important for people running power plants. They don't talk about efficiency. They talk always about the heat rate, the BTU per kilowatt hour. And that number makes sense that when this number is low, should we be happy or sad? When the heat rate is low, should we be happy or sad? When this number gets smaller, do we get happy or do we get sad? You get very happy when this number is low. Why? Because so what makes them happy? When it's 9,000, 8,000, they get really, really happy. Why? Because when it's 9,000 BTU per kilowatt hour, the BTU is what they pay for the natural gas company. They don't own the natural gas company. And the kilowatt hour is what they pay for the people. Okay? What they get from the people. So what I'm trying to say is that when this number is small, that means they are paying very little for every kilowatt hour they are using. Okay, does this make sense? So when this number go up from them, they get panicked because now they are not making money. So we are selling it for 11 cents the kilowatt hour, and they are paying a lot of money because they are using a lot of BTU. And that happened when the power plant run at partial load. When they're rather running at full load, when you run like they say, we don't need all this power, go down. When they go down, the efficiency dropped. There's plant, those steam power plant are designed to run at full load. So they don't get, so once you cross 10,000, 11,000, that is horrible. So this one is 22,000. That is really, really horrible. But they are not paying for the BTU, right? So when this eta thermal is 15%, that's not really killing them because it's not like they are burning natural gas. They are just using ground hot water, right? So again, as like all renewable energy, you don't really care about this number. You care about what is the price of the equipment and whether I will be able to get the money at the end of the life or not. So it's again the price per kilowatt hour over the lifespan of the project, right? but the efficiency sucks. Like regular power plant should be, the steam power plant drinks is like 40%, not 15%. And the one in Owasso is like 65% because they are running combined cycle. They have gas turbine on top of a steam power plant. So their steam power plant kind of running on the exhaust of the gas turbine. So their steam power plant is running for free, kind of. So that's why they hit 65%. Okay. Now, what is the price per BTU? We know that they pay kilowatt hour. They let us pay 11 cents. How much they are paying for BTU? So actually, just today, actually in the news, I was reading how, so the biggest exporter of liquefied natural gas, they sell it to Japan and Korea. South Korea is Qatar. Qatar is a small semi-island in the Gulf, Persian Gulf. And they are the largest, they are floating on top of natural gas. So they are selling every 1 million BTU for $4. Okay, on the delivery. So we deliver the ship to you with liquefied natural gas to Japan or to South Korea, and they sell it for $4. Like here in the US, if we sell it liquefied, it's like 7, 8. So they cut the price a lot so that they can. Just today, they announced they're going to cut it down because they want to try to take the market from other people. But that tell you what is the order of magnitude of 1 million BTU. So 1 million BTU is sold around like 4 to 6 to 7 to 8. 1 million BTU, okay? So if we make this, so I said a good number is 10,000 BTU per kilowatt hour. So for 1 million BTU, how many 10,000 in 1 million? 100, right? So if million BTU is $4, then 100 BTU would be 100,000. Sorry, 10,000 BTU would be 40 cents or 4 cents. Right. So they will get it with 4 cents from Qatar and sell it to us for 11. So that's how electric power plant. But over here in the US, probably they are paying 8 or 7 to the natural gas company. So they pay with 8 and they sell it for 11, so they can make 3 cents maybe in kilowatt hour. Okay, but you can see how when that heat rate go up, and it's not 10,000 anymore, it's 11 and 12, that cut in their profit. So then it will cost them, you know, for every kilowatt hour, it costs them 11 cents and they are selling it for 11 cents. Like, doesn't make any sense. You got me? Okay. So because of this, I also ask a lot in the exam about the heat rate. And you shouldn't really panic. All you do is calculate the efficiency, like we always do in all the cycle, and say the efficiency, the heat rate is 3,412 divided by the 40%, the 30%, whatever your eta is. And that will be your heat rate in what unit? BTU per kilowatt hour. That's the only thing that you need to remember. Okay? Heat rate 3,412 over eta thermal. Okay? And why? If you do the conversion, you will see how a kilowatt hour is 3,412 BTU. So you are basically converting from dimensionless to those units. Good? Okay, so he say here the thermal efficiency 15% does not include losses and bumping requirement. Okay, and so he's saying that those things could actually lower you to even 10% when you really count for them. So now let me look at this picture in detail and tell you what happened exactly here. Once you leave the condenser as saturated liquid. Okay, and why you'll be saturated liquid? Because they pull it from the bottom, they pull the liquid from the floor. So it is gonna be liquid. You're not gonna get anything that is like bubbly, or you're gonna get saturated liquid at 5. Okay, then what? You bump isentropically up to 6, 5 to 6, okay? And then you cool down, right? So you would cool and hopefully you cool lower than the steam that you want to condense. So when you go to that cooling tower, there are two kinds of cooling tower. There is wet cooling tower and there is dry cooling tower. The dry cooling tower, the water go into pipes, never leave the pipes. Air with big fan, sometimes the fan is on the top, sometimes the fan is on the side, but the fan is blowing cold air on the water in the pipe. That is a dry cooling tower. So you never lose any water in the cooling tower. And you get cooled from 6 to 7. Okay? And once you are here at 7, you spray the water in the steam. So that kind of condenser is called direct contact. Direct contact condenser. Because rather than, what is the other condenser would look like if we don't do this? Like the cooling, the condenser in Jenks power plant, for example, how does it look like? The water here go into pipes, okay, and the steam condense on the outside of the pipes. So it will look like, this. There is this big place that is actually sitting under the turbine. So the turbine send the steam down, and over here, a lot of pipes, okay, and those pipes are running cold water in, hot water out, while the steam that's sitting over here kind of condense on it, making film and drip, 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 drip. And so the floor here is filled with saturated water. And then he take the water down. Okay, so that would be this point 5. H5 is here. Okay, make sense? So now when you have a condenser like this, then this water can be dirty water, right? This water can be dirty water. This water can come from the river into the pipes, leaving back into the river. And when I was undergrad, one of my internship was in a steam power plant like this, and we used to clean the condenser every now and then by sending rubber ball. And they send rubber ball into the pipes because the pipe will get mud from the river. And you send those rubber balls, small one, then bigger, so that they can scratch the pipes and take the mud out. Okay. And actually, there's a lot of companies that make more sophisticated things for nuclear power plant condenser too on pipes, but it's not ball. It has like special shape, so that. But the whole idea is you send things that scratch the surface of the pipe and clean it in the process, and you collect them on the other side. Okay, so when it's like this, when it's dirty water, then you don't mix with the steam. This guy go in a pipe and this guy go in. But if it is a clean water, you can actually, and so in order to be clean water, you can see how he's like doing it in a closed pipe so that the water is always clean. Then he can spray it in the steam. And so what's nice about this is that instead of having a pipe where the steam is condensing and you have a lot of pipes so that you have a lot of surface area, you spray water, and every one of those water droplet is like a surface for the steam to condense on. So you can imagine how much extra area you have. Depending on how small those droplets that you are spraying, you can have tons of surfaces for the steam to condense on. Okay, so the bottom line is that the 7, when the 7 come back in here, 7 and what? 7 and 4. 7 and 4 get mixed together and the output become 5. So 7 and 4 generate 5. Okay, and so he could ask, and he will ask in other problem, how much water is needed in the cooling tower? And how do I do that? If he said, how much water is have to go here? To do what? To take the steam from 4 to 5. What's your M dot cooling water? How do you guys do that? The first law of thermodynamics, which would be the enthalpy difference. Exactly. Good job. So I am saying that the condenser job is to take 4 to 5. And he do this by mixing 7, right? So here's a direct cooling condenser, stuff coming at 4, supposed to leave at 5, and 7 is being sprayed from those nozzles. Okay, so if I do first law of thermodynamics between what? Between this and between this, right? So I would say m dot 4 times h4 minus h5. This is how much cooling happened. So h4 minus h5. This heat that the steam lost must be equal to m dot 7 times h5 minus h7. Does this make sense? Whatever the cooling water is losing is what whatever heat the steam is losing, 4 minus 5 times n to 4, is what the cooling water is gaining. M dot 7 times h5 minus h7. Right? You see how there's like, this guy is being heated while this guy is being cooled. 4 go to 5 by 7 rising to 5. Okay? Like you are really rich and your friend is really poor. And so the money that you give to your friend is how much money he will be able to get. So 4 being the rich guy, 7 is the poor guy. And so 4 give him his joules so that 7 can, both of them leave at the end of the day by 5. Okay? So he didn't really want to go through all of this. Huh? He didn't want to go all of this, and he said, you know, everything is here. 4, 5, and 6, and no, sorry, 5, 6, and 7 are here at this point. But this kind of calculation is important to figure out how much m dot is needed to go to the cooling tower. And then you'll be able to calculate the surface area of the cooling tower and how much air does it need to cool it, you know, all those things. Good. All right. So now that's it. I'm going to ask either the thermal efficiency or the heat rate or how much steam is needed to generate the 10 megawatt, right? The other system is when you are not lucky. You don't get steam. So what do I get? I get hot water. Really hot, but it's saturated liquid, not saturated vapor. So rather than having it on the HG side, I'm getting it at the HF side. Okay, so it's still valuable, right? And they actually still use it. This would be called flash system. Why do we call it flash system? It's going to be like this. See the water coming in at point 1. That point 1 is here. So rather than being here, it's coming here. But look how high it is. Like really, really hot water. Really, really hot water. Huh? So rather than coming like here and we throttle it, no, it's coming over here. So water is nice, but I cannot run turbine with water. Okay, that if you want to generate power out of this, it's not called a turbine, it's called the expander. And our technology of making expander is not really that great. So our expander don't work that efficiently. Okay, so turbines is way better. So to get power, to run a generator, you need steam. So how do I get steam if I'm having liquid at 1? I reduce the pressure. So I send them into a flash tank. It's a tank under vacuum, or at least the pressure here is lower than this pressure. So whatever pressure you got over here, this tank has lower pressure. So what happened when you go into a flashing process? This line is constant What do you think? Excellent. Constant enthalpy again. That chapter is really nice. Everything is constant enthalpy. So you go from 1 to 2, huh? 1 to 2 to 3. So 3, now once you go into this chamber, and so that chamber is not just like big tank. Sometimes they make it like a venturi so that the pressure can really drop as the flow is going through it. But the point is you will end up having some liquid and some vapor going from this high pressure that he will specify. He'll tell you, we get it at, 20 bar, and then we drop it to 10 bar. Okay, how much is steam and how much is liquid? If let's say this is 10 kilogram per second, how much of those 10 kilogram per second become actually steam ready to go to the turbine? How do I calculate that? Excellent. So for those who cannot hear Denver saying your X, your quality at 3, and I can get the quality at 3. How can I get the quality at 3? Because I know the H. H3 is H1. So if I know this H at 10, let's say this is 10 bar, I know H3 equal to H1. And I also know this H from the table and this H from the table. Then that equation that we wrote, how H3 is X3 times HFG plus HF, I will be able to calculate this X. What is that X by definition? If say I calculated this X and it turned out to be 15.15, I know X is 0 over here and X is 1 over here, but what is X? X is actually, by definition, is what? M dot, yeah, X is M dot. Is M dot vapor over M dot total. So when you get X3 equal 0.15, that means 15% is M dot vapor and the rest is liquid. So that's all we need. So we need this X. So let me write this so that we can see it clearly. Because that is really what is hard about this category of problem. When you have a flash tank and you are leaving here, you are coming here at 1 and you are flashing like this, and notice how they always make it dotted. Why? Because it's not isentropic, right? Flashing. So constant enthalpy or throttling is not isentropic, obviously. If it was isentropic on a TS diagram, we will see it going down. But processes that are not isentropic, we make it dotted because we don't really know how it will go. That's the significance. If it's isentropic or constant temperature or constant pressure, we can plot it. We know where it goes. So this is 3, and this is 3F, and this is 3G. And so what I'm trying to say is that you need to remember that X3 is going to come from, how it's going to come from? It will come from this equation, that H3, which I know because it's the same as H1, is going to be H3F plus X3 times HFG, which HG, H3G minus H3F. So from this, you can get your X3. And you need to remember that this X3 is M dot 3G over M dot 1. So if this, for example, is 0.15, that means that 0.15 of the mass is going to go into the turbine. Okay? Make sense? Good. So the rest is the same, exactly. Huh? He send it to the turbine, we get the H's, condenser, take you all the way to this, and look at here, like saying 5 and 6 are here, basically. The pump is nothing. 5 and 6 are sitting in that place, and 7 go down like this, right? But see, this time he's smart. Look at this, what he did this time. He's sending it into the ground without cooling it first. And this way, the amount that go into the cooling is only the amount needed for the cooling. But the rest of the flow rate just go back to the ground. Right? Very good.
Sir, in that diagram on stage 6, is there a valve? How is it altered? How much goes up and down?
That's an excellent question. And yes, there must be a valve, of course. Yes, definitely.
Okay,
And when
thank
you think about it, that part does not really require that much pressurizing. I mean, to go through the pipes of the cooling and then back into the nozzle, he just need to be a little bit slightly above 5. I mean, how much pressure loss is needed to go into a pipe and into a nozzle? But to go back again into that pressure, that is huge pressure, right? So the pump is built really to go back to that pressure, P1, so that you can go down. So 6 and 1 are the same pressure, right? And there is also another pump over here when you think about it. Because what happened to that prime? So we had steam going to the turbine, depending on the X. And how about the liquid? What happened to the liquid accumulating over here? Huh? Yeah, you need another pump like this, right? And that pump is gonna take it down. And again, all those pumps are neglected in those calculations because they think it's too small. But to be accurate, people should calculate them. But we will stick to the book and say, I just need you to write to me that you know that you are neglecting the pump. I just don't want you to forget about it. I want you to be, aware of the fact that yes, there is a pump, but I'm neglecting it. Okay. Good question. Excellent question. So you can see the solution, right? There is nothing surprising here. You go for the H's the same way we said, right? And M dot turbine, how M dot turbine is, the X of the flashing chamber time M dot coming from the well. So only this X time this will go to the turbine. All right? Eta generator to calculate the actual power output, electric power output. And okay, one time also I just asked them, I gave them this and I told them to plot the TS diagram. And to my dismay, not that many people even try to attempt the problem. So, I mean, why is that hard? It's just like 2 flashing chamber, okay? And so what he do is that after the first flash and he got his steam and that steam ready to go to the turbine, the prime is just like too high to be thrown, too valuable to be thrown. So he's saying that if I'm flashing like this and I get this T5, I mean, this is still really hot water. Why would I throw really hot water back into the well? So sad. So rather than throwing it away, what does he do? Another flashing chamber, right? That does what? Give you some prime here and some steam here at 7. See? And that steam at 7 mix with the first turbine that's at 9. And the results is 10. So it's here. Look at this. So the first turbine 4 go to 9. And then the vapor from the second flashing is 7. He get mixed. 4 and 9, 7 and 9 get mixed together and become 10. That is the one that go into the 7 and 9 got mixed together, and the results 10 is the one that goes through the turbine. Okay, so let's go through all the H's because that's what we need to do, right? To calculate those things. How can I get H1? He will tell you the pressure, you get HF at that pressure. And then H2 is the same as H1 and H3 is the same as H1. How do we get X3? the H and HF and HG. You'll be able to get X3. Once you know X3, then you'll be able to calculate M dot going in here. Right? So this is H saturated, HG, and then you do the same thing. You go first isentropic, and then you do the isentropic efficiency, you get actually H9. Same thing happened on here again, one more time, right? And you end up with 7, the same way you end up with 4. So now between 7 and 9, how do you get H10? Help? What is H10? How can we calculate that? Say that louder. M.9 and M.7, I know them, right? So how can I get H10?
M.7 plus M.9.
M.7 plus M.9 is M.10. Yes, but I want H10. I don't need M.10. I know M.10. I need H10. How do I get H10? Excellent. Denver is saying apply the first law of thermodynamics. It's simply a simple mixing problem. Here is M.7 coming with H7, and he's going to mix with the exhaust of the first turbine, which is M.9, leaving at H9, and both of them is now going to the second turbine at M.10, H10. So if I think, well, this is my control volume, and the first law say energy in equal energy out. So M.7 H7 plus M.9 H9 equal to M.7 plus M.9, because that is the total mass leaving time H10. The only thing that's unknown here is H10. You will be able to figure exactly how much is coming to the second turbine, right? Good job. So that's how he can get H10. And so he go again H10S, and then the efficiency get H11, and the rest is the same like everything. But I'm telling you, last time I gave them the sketch and I just plot the TS diagram. They didn't plot it. So I need you guys to learn how to plot this. This is very important, to sketch the cycle on a TS diagram. Or like if I give you this, can you plot this for me? You know, so you look to this, or you look to this one and you can tell, it must be one single flash. How could you tell? Because he's coming from here and the liquid and he's dropping like this. Right? So I think it's important to be able to switch between the TS diagram to the equipment sketch and vice versa. Okay. Good. So now the third method, which happened when the liquid coming from the ground is hot, but not that hot, or it's just too salty to make steam out of it. So it's not steam like hydrothermal, we're ready for the turbine, or it's not very hot water that we can flash it and get some steam out of it. No, it's just like really bad quality or not that hot. If you flash it, if it's not that hot and you flash it, how much you will get? You'll get nothing. I mean, you get 1% vapor, it's not worth it. But the temperature and the flow rate is big enough, there's a lot of joules. So what people do, there is actually a system like this all over the world. And so for those systems, they call it a binary cycle. Why binary cycle? Because there are two fluids in this cycle. There is the salty brine that come and go, and you just send it into a big heat exchanger where he meet the second fluid. And that second fluid could be a clean steam going through, or you can let your imagination go wild and run it over propane or ammonia. or anything that will boil at that temperature. Say this water is only 100 degrees C, not 1000 degrees Fahrenheit. Just 100 degrees C. You will make something that will boil at that. And you become vapor. Vapor is ready for the turbine. Get some work. Turbine take you to the condenser, and the condenser pump, and you do the cycle. Of course, the condenser has to be cooled with another liquid, right? That go between the condenser and the cooling. And he does not have to be open cycle. I mean, he could just be a closed cycle. So this is actually the easiest system ever to solve because it's like really the standard Rankine cycle. So those binary system, you will have your Rankine cycle running like this, whatever your fluid is. So here is your 1, here is your 2, here is your 3, here is your 4, and your brine is actually doing this. No, your brine is doing this. Your brine is doing this. He's coming hot and he's leaving cold. And what is that? That is the cooling fluid in the cooling tower. So this is the cooling tower fluid. He get heated, and then once he leave you, he go back again to the cooling tower and he get cold again. And then he go back again to your condenser, go up. So he's like up and down, up and down. And the binary, the brine coming from the ground come like this and leave like this. And then you send him again to the ground where hopefully he will do what? He will get heated again. Okay. So, and the Rankine cycle that's driving this is basically all it need is, Q edit that will come over here and send Q rejected over here. Get heat from the brine and reject heat to the air. Okay, and of course, work net is what? Q added minus Q rejected, right? So I mean, that is a sketch, and it's a basic Rankine cycle. So there's something called enhanced geothermal system. 1 year I just asked them to make a sketch, and one guy I still remember, he made it perfect. I mean, he made it with, like, he copied every single crack in the rocks. It's too much. You spend too much time. I just need a sketch of what's going on. So what's going on? This is a system or places where there is no water. Okay, there is no steam, there is no liquid, there is no brine, there is nothing liquid in there. There's just hot rocks under you. So what do you do? I mean, it's hot rocks underground. It's like a really loss of availability if we don't do something about it. So what do? They send the water in, right? And the water hopefully get heated, and they help the water get heated by fracking, kind of like they break the rocks so that the water can find its way in, and then they pull it back. They pull it back in here. So water get in, hot water come out. Okay, so hot rocks, and it's basic. So engineered fracture system. So Dr. Raman Singh over here was Dr. Pankash, Serene, and another professor from TU. They got a really big grant just earlier this year from the Department of Energy about how to optimize this fracture process, how we can make it super cheap energy-wise. How you can really break what can be done in order to make breaking, because it's not just important for oil, natural gas fracking, when we break the rocks to get natural gas out, but it could be also really good for something like this. So they study, between the three of them, what's the mechanism for breaking those rocks easily. Okay. So what do we call this? Enhanced geothermal system. I guess it's a geothermal system, and you enhance it by allowing more surface area to happen. So I could just say, plot a sketch of the EGS to be mysterious. And you're like, what is EGS? What the hell? And it's enhanced geothermal system. Okay, good. Now, this is fictitious. This doesn't happen yet. Then this is basically saying, what if we really dig down to the magma level, right? Where the temperature is like really, really high. Can we make profit out of a system like this? And they are saying, yes, you can. Well, in some places, the magma can really rise up. And like Sandia plant concept. So if you can dig that deep, they are saying that maybe you can, not just for heating, because that costs a lot of money. It's not worth just for heating. But they are saying, what if we can also make hydrogen out of that place? Like we send the water and the water will come back to us as hydrogen. Then we just like fill the hydrogen pipes or hydrogen, and then we use it as a fuel. So hydrogen fuel is considered as part of the future too. Like people think maybe in the future, all that wind and solar, we use it to break water into hydrogen and oxygen. And then the hydrogen is what we run our power plant with and so this way it works as our storage. Okay, so when solar and wind are available, rather than storing in a battery, you store it by turning the water into hydrogen. And now the hydrogen go into your natural gas pipeline, become now hydrogen pipeline, and you can basically use it. Yes.
On that process, like, we're using this water to create hydrogen. That when we burn that hydrogen, it turn back into water.
Yes, hydrogen burn back into water. That's what, when you see the space shuttle before it retire, that big white cloud coming, that is really cloud. That's really H2O because they have hydrogen. Hydrogen is like the best liquid rocket fuel ever. But it just, from impulse point of view, how much force, how much thrust you get from it per unit mass flow rate. But the problem is it needs to be very cold. So that foam tank, that orange tank is really, really cold, right? And Dr. Ranji over here in his lab, they actually have a lot of research over many years about how we make, and he got funded one time from NASA, think about how we make tanks very light to store gases, like natural gas for cars, and hydrogen and stuff. So there is a lot of material too in like how we can make those tanks take high pressure and store at very cold temperature. But anyway, so not that many places have the magma so close, right? And also this is just a concept. So now what is really available, and I don't think we have a lot of time for it today, but what's also available for us, the fact that, and I saw you the chart at the beginning, in Oklahoma over here, the ground is actually a little bit hotter than if you go to Michigan or Illinois or something. So what do we do with it? Well, in the winter, when we are trying to heat our houses by the air, and the air is pretty cold, right? Wouldn't it be nice if we heat our house with, and that's what you guys are going to heat the swimming pool with. So an HVAC machine, or a heat pump. This is you, this is the house, and this is the outside. Is 2 units, This is the condenser, and this is the evaporator in the summer. Okay, and so in the winter, so in the summer, that's what happened. In the winter, this become the evaporator, and this become the condenser. Okay, so they are connected to each other through a compressor and natural gas. So in the compressor is actually sitting over here. So they connect by a compressor and a steam by a throttling valve. So how does this cycle look like? This is the Weber combustion cycle, and really a good way to plot it is on a pH diagram. Pressure and enthalpy diagram. It looks like this, and there are two pressure, B condenser and B evaporator. And again, the condenser would be inside, the condenser would be inside in the winter and will be outside in the summer. Okay, how do they do this? The exit of the condenser has a valve on it, and that valve say, take that hot exit. So by the way, he go like this. The condenser take you, and this is constant S. This is entropy, like isentropic compression. So that exit of the condenser, which is really hot, that's the hot point in the cycle. You would basically say, winter, take that hot, send it to the house, make the house warm. Cold, it's like it's summer, take that hot point out of the condenser and let it go outside. Okay, so that we can heat the outside in the summer. So we heat the inside in the winter and we heat the outside in the summer. Now, the exit of the condenser go into a throttling device. So in a pH diagram, it will look like this. So that is the lowest point in the cycle. So 1, 2, 3, and 4. So that very cold 4, that's what go into your house in the summer to cool it. Okay? So the house would be sitting like this, and say he will be sitting here at like 70 degree Fahrenheit, but the refrigerant over here, he's coming at say like 50 degree Fahrenheit. So of course he will cool your house. And then when he go outside to the condenser will go out, and that ambient, say a very hot day in Oklahoma, like say 90 degree Fahrenheit. But he will be leaving at, maybe 120 degree Fahrenheit. So he will still be cooled. So, I mean, the first time I saw this cycle when I was undergrad, I thought that this is genius. I cannot believe how great this cycle is. Like, I want to meet the guy who first came up with this idea. Because he's basically solving the problem that heat always go from the hot to the cold. So how do we convince our house that is 70 degree in the summer to heat the 100 or the 90 degree outside for an ambient? And the guy was like, okay, no, we always have to have something hotter than the cold one that for the heat. So what you need to go inside the house, you need to come a little bit colder than him. And when you go outside, you need to be hotter than the outside. And so how do we connect? Let's use a compressor. Let's go to the throttling device. The cycle is done. And the refrigerant heat up, right? And go to the condenser and cool down with a evaporator, or sorry, with a throttling device, and go to the evaporator. And he's always cooling one side and heating one side. So now, if that temperature range is super big, like no, your kids are saying, no, we don't want 70, Daddy, it's so hot. I want it to be 65. And it's like really hot day in Oklahoma, 110 or something. Let's imagine 100. We never get 110, right? Did we ever get 110? Yeah. So let's imagine 110. Then the condenser and the evaporator and the condenser need to be even hotter than those two guys. And now the compressor need to do this and need to do this. Can you tell from the drawing what is the problem? See this part, this H4 minus H1, this is how much Q he's pulling, right? If I ask you how much is the evaporator is pulling from my house, you would say this Q, let's call it Q low. Q dot low is going to be what? M dot refrigerant multiplied by H1 minus H4. That's how much is pulling from my house, right? And you see how that when the range get bigger and bigger, I mean, if it was running like this, see, I got all that. But as I go up, I get very little. So this cycle performance is quantified in terms of not efficiency, they call it COP, coefficient of performance. And that is QR minus work divided by compressor, work compressor. It's the output over the input, but it's not efficiency because sometimes it will be more than one. Q dot R could be work more than the work compressor. Okay. So, but you can see as I make the temperature range bigger, what happened to the COP? It will deteriorate. So because we are running out of time. So if the outside was not as cold, huh? And the outside over here, if that range is not that big, life would have been easier, right? So to shrink that difference, rather than using the condenser or the outside unit, rather than being in top of the ground with air that's very hot in the summer and very cold in the winter, if you bury this in the ground, he will actually not have that much range because the ground is, especially in Oklahoma, in the winter is warmer. So rather than trying to get heat from, -5-degree air, no, the ground is sitting at 40. So that's pretty cool. Let's get it from the ground, right? So that is, and I guess we'll talk about it more next time, but basically that is the point behind ground source heat pump. And the capital in Oklahoma City is actually cooled like this, cooled by heat pump that is connected with not with air, but with the ground. And the big Catholic church that they just built in Stillwater, the whole HVAC is connected to the ground. It's all ground source heat pump rather than by air. And it's also less noisy because you don't have those fans. You have pumps that send water in and bring water out. But of course, so this explained what I was just saying, right? And this is the COP. What is a COP? Output over input. But of course, to get all that area to cool, you need big network or big area. So you cannot just dump the water in one place and pull it. It will not cool. Need bigger area, right? You need different wells so that you can distribute the water and pull them back. So it costs money to build something like this. So, but for big building where that load is like a big deal, like a big church or the Capitol, electric bill is super high, the saving will be able to make you get back your money in a very short time. But for my house, if all my electric bill is like $10 or like whatever, $100, how many years will it take to make the difference? Okay, thank you so much. I'm sorry I went overboard.
Thank you, sir.
Bye.